quickly. I am going to also start the next section. I won't do the whole thing today, and then we will finish it on Tuesday. But this one is saying to express as an integral. So it's telling me to write an integral. The solution to this is called an initial value problem. So it's saying dy dx is equal to secant x. Y of 2 equals 3. Alright. But I am solving this as an integral. So I don't even have to have like an actual value of x or anything that I'm solving. I'm writing an integral. Dy dx is the derivative, right? So the integral was what we did before the derivative. Remember from the fundamental theorem of calculus. A derivative and an integral, what happens if you do both? They cancel. But we replace x. So think about this x replaced whatever my variable was. So maybe it was a t. Okay, then we know it has to go from a constant up to t, right? Or not t, x, because x was the variable we plugged in. Do you know where this one's going to start? 2. Okay, since it says initial value, we can say that it starts at 2. So let's check. If I did the derivative of this, do I get secant x?
Yeah.
Okay, the other thing I'm telling you is y of 2 has to equal 3. Now you could have started this at 0, but the benefit of starting at 2, if you integrate from 2 to 2, what happens?
0.
It's 0. If I want to get 3, I could just do a plus 3 on the end. Okay, this is going, the integral is just this part. My variable is t, so d dt. So it's basically saying you do the integral, you add 3 on the end. It's not a unique solution, it's not the only solution, but it fits the requirements. If you did the derivative of this integral, they would cancel, replace the t with an x. What's the derivative of 3? 0. So it fits that requirement. Second requirement, if I plug in a 2, if I integrate from 2 to 2, I have to get 3 out. Well, the integral from 2 to 2 of this is 0 plus 3 is 3. So we wrote a integral that solved both of those problems. It's really just assessing the thing applied the fundamental theorem of calculus there. I'm going to jump to a problem. Let's go to the very last example.
Whoa.
13. So if I wanted this one, my integral would be from where to where?
T. I want x, right?
What are we going to integrate?
Tan t.
And we would put a dt with that, right? If you have an integral, you need to do something. Okay, so let's check. dy dx. If I did the derivative, do we get tangent x? The other requirement, when you plug in 1, you have to get 2. So do plus 2.
That's so silly.
Isn't
So
that
silly.
silly? But it just uses our fundamental theorem there. Alright. Let's work backwards. G of x is the integral of this function. So g of x is the integral from 0 to x sine cube t dt. I want g prime of x. What's the derivative of that?
Opposite of negative cosine.
3 cosine.
Sine cube x.
Okay, this felt like a trick.
No, this is from yesterday.
I didn't know what was.
Because I asked for the derivative. The derivative cancels the integral. Just replace your variable with the x.
Ow.
Silly goofy goober.
Alright, let's go backwards. Problem 11. If I asked you to find the derivative of this one, oops, there should be a dx on the end of that. Pretend there is.
Radical equal Q squared plus 25.
Because the derivative cancels our integral. Alright. Is that okay?
A little confused about 10.
What?
Okay.
What do you mean?
This is probably going to be the last one I do today. Problem 9 is not that the antiderivative is so bad, but the numbers when you plug in are a little uglier than I anticipated when I made up that problem. So I'm not going to work that one out. It's just going to be, it would not be something I could give you without a calculator, for sure. But this one,
That's what the else.
if I want the total area bounded by x cubed minus 9x and the x-axis. So this, the total area, we know area under a curve is an integral, right? But x cubed minus 9x, I didn't give you like definite starting and ending points, right? So we have to figure out when this is equal to 0. We can add that to get x squared minus 9.
0 plus minus 3.
Okay. Because I said total area.
Oopsies.
Not what I meant to do. That. This graph hits the x-axis at -3, +3, and 0. If you are in between -3 and 0, so if you have like a -1, -1 cubed is -1 plus 10, that's positive. If you put in a 1, you get 1 minus 9, which is negative, and that's positive. So the graph looks like this. If I just integrate from -3 to 3, it's going to say this is positive, this is negative, it's going to subtract them off. But when I say total area, that's meaning the absolute value of that area. Okay, because I went to not subtract off negative, I went to add it to it. So from -3 to 0, we already established it was positive, so the absolute value wouldn't change it. From 0 to 3, we would have to do the negative. Alright, if we just integrate the normal one, it's going to subtract it off. But because I said yes.
Okay.
So antiderivative of x cubed, 1/4 x to the 4th, minus antiderivative of 9x,
9x squared.
-1/4 x to the 4th, plus 2.5 x squared. Alright, so if I plug in my 0, I get 0, minus -3 to the 4th is 81 over 4, minus 81 over 2. If I put in my 3, and so if I do that, I get 81 over 4, 81 over 4, 81 over 2.
Why do you have 81? Why do you have 81?
Hmm? I did this. 81 over 4 minus 81 over 2 is negative 81 over 4. The opposite makes it the opposite. Alright, is that okay? So that's the answers next week.
Oh, there's a lot of that.
Okay. So indefinite intervals. I've actually kind of already told you this because it's shorter to write, and so I've been doing it some already. We know an interval is an antiderivative, right? And definite interval is when you have that antiderivative with numbers to plug in. And an indefinite is when you don't have the numbers to plug in. And so that's just when there's no limits to plug in. So in that case, what do you have to write on your final answer? A plus c. So if it's indefinite, you're getting a function for your answer. It's still going to have x's in it. If it's a definite interval, you have numbers to plug in, so your final answer is a number. Right? That's really the only difference. So we have done these.
Oh,
We are just continuing to practice these because in the next section we're going to learn some new integration techniques to allow us to integrate more difficult things.
whoa.
So we're practicing this a little bit more.
There's more difficult things.
So if I ask you to do this integral, that just means the antiderivative. What is the antiderivative of 10x to the 4th?
2x.
Alright, you add 1 to the power, multiply by 1/5. Minus 2. What has a derivative of secant squared?
Tangent.
Look at you guys.
Yeah.
And then, what else do you need?
Let's see. Oopsie.
Cosine makes negative sine, and sine makes cosine. Yes.
Okay, but here's the problem. Can we do the quotient rule in reverse? No.
Oh.
So it's cosine.
So I need to
So
think
we
about
break
this.
it up.
Okay. Sine squared
That's
is like
tangent.
sine times
What's
cos. Oh, sine times sine.
So you get
Oh my gosh,
tangent
it's
and secant.
cotangent times cosecant.
Yeah. Tangent, cosecant, and then you do the thing, and then that's just cosecant. Or negative cosecant.
Okay. Again, we can't do product rule in reverse, but we can ask ourselves, does anything have a derivative of cosecant cotangent?
Oh yeah.
The derivative of cosecant is negative cosecant to cotangent. So this would have to be a negative cosecant theta
Plus C. Oh my gosh.
Wait, negative
I'm cooking.
cosecant.
antiderivative of x cubed, antiderivative of 6x. Okay, 3 to the 4th is 81 over 4 minus 27 minus 0. So you get negative 27 over 4. Is that okay?
Yep.
Alright, you ready for a challenge?
What's a challenge? Oh, that's not a challenge. Oh. It's not an actual. Wait.
Okay, this
Wait a
requires
second.
something we haven't seen in a while.
It's not a natural log. Wait, do those cancel?
Wait, does
No,
that,
that's an, oh.
does that become 3x to the negative 2 plus 3?
Okay, so let's start with the 2x cubed. What's the antiderivative of 2x cubed?
1/2 x to the 4th.
Minus the antiderivative of 6x.
3x squared.
Okay, this one. This is like 3 times 1 over x squared plus 1. This probably isn't overly familiar because I didn't make you memorize those, but remember way back when? Like way back when, before Christmas, we had derivatives of inverse trig functions. We derived a few of them, but I told you I wouldn't make you memorize the formulas. This is actually one of them. So I probably wouldn't give you one of those on your homework or a test, but it seemed like fair game for a class example. I don't remember exactly where it was in the book. We looked up inverse trig functions. There was a table.
I remember talking
I remember
about
the
it,
table, yeah.
but
Spinal stuff in the table.
I don't remember which one that is.
Oh, I thought you were a table.
That's cosine.
That's cosine? I'm thinking it's
Probably.
sine.
I get a 1/6 chance.
Yeah, I'm thinking it's actually sine, Jim.
260.
It's not a I think that's
No,
cosine.
259.
I think you're wrong.
Oh, I do remember this.
Oh wait, no,
I knew it
that's
was
cosecant.
I believe that's cosine.
I got cosine and I got secant, and you got sine and cosecant.
Yep, yep.
Oh, no way that's tangent.
That's winning odds. No, that's not winning. That's winning
I
odds.
can't remember which section I covered it in.
One third to
I'm gonna
one
go
third.
I want to say
I'm gonna go with
second
cosine.
one
It
though.
was
Yeah.
derivatives.
Hey, that increases my winnings.
What? No.
See my cosine.
I also win.
That increases your
Oh.
losses
Yeah,
too.
That increases my
Winnings and losses.
win.
You would think I could find this.
No, I have the same losses. You guys have.
You're being
minimal
slow, Harden.
winnings. This is
Two-thirds.
Samantha's, but same difference.
Okay, here we go. Page 214.
Oh, did we get it?
Look at the red chart on the bottom of page 214.
Which one is it? Andy?
Oh,
Oh, here you go.
Tangent. 1 over x squared
We all
plus
lost.
1.
No, we lost all of our money.
You lost all of your money.
Yes.
You're looking at these. The cotangent one has a negative. We want the one that doesn't have a negative.
sorry, tangent, guys. You both of y'all were like.
Still wrong.
So that is your tangent.
Oh.
inverse.
Someone said tangent at one point.
No, we said no way it's tangent.
Okay, so now we have numbers to plug in. 2 to the 4th is 16 divided by 2 is 8. Minus 12 plus 3. I do not know tangent inverse of 2 off the top of my head. That means when is tangent equal to 2? That's not a nice angle.
What?
If you put in 0, those are zeros. Plus 3. Tangent inverse of 0. When is tangent equal to 0?
0.
0. So we just get negative 4 plus 3 tangent inverse of 2.
Whoa.
Okay, not super nice, but just a good reminder. We did have those, I just didn't make you memorize them.
So we can't turn it into 3x to the negative 2 over.
No.
Dang.
Because if you did the chain rule on that, you would have another x appear in your derivative. And that's why it wouldn't work.
Oh man.
But in the next section, we'll talk about other options for that.
Well,
Alright,
How do we find that the derivatives of the inverse of functions? Like, how do they?
we derived the first 2, I think, when we did them. If you look back in your notes, we did them.
I know they're at home.
What would you have to do before you could do this antiderivative?
Divide by
divide by t to
Get
the
the square.
square.
each term.
So each term by t squared. So that's 2 plus the square root of t, or I'll write that as t to the 1/2, minus 1 over t squared, so t to the negative 2. So antiderivative of 2, 2t. T to the 1/2, so if you add 1, that's 3/2, you need a 2/3. Okay, here, add 1's negative 1, so you need a negative in front, which makes it positive. Nine to the 3/2, so that means the square root of 9, which is 3. Cubed is 27, times 2/3 is 18.
Wait, why is that?
What's 36 times?
Hang on,
9?
why is that
Thirty-six.
one still
3, 2,
positive?
4.
It's a negative
So
1,
it's
so it's
325
325 over 9
minus
minus
3 plus 2/3, which would be 11/3.
11.
So,
and then multiplied by
so that would
3.
be times 3, 33 9.
329 minus.
So that would be 2,
292.
292.
329. I thought it was 310. 392.
Oh, I added 1.
Yay!
Wowza.
Okay.
That's a nice pretty number.
I am going to
Give us homework.
Give us all the homework.
Keep going.
Okay,
Teach the rest of the lesson.
give me 5 more minutes and then I'll stop.
Okay.
I just want to run through, I'm not going to work out any more examples, but I want to talk about what some of these applications mean. So the whole point of this section is talking about net change. We know, we talked about it in terms of areas. right? An integral can give you the area under a curve. But there are other applications as well. We know derivatives are rates of change. So think about if you go backwards from a rate, you're getting an amount. So I have a lot of different scenarios on here. If you're talking about volume, okay, V prime is the rate that the water is flowing into a reservoir. So if you go backwards, then this would give you the amount of water that came in between two periods of time. So V prime is the rate of change in the volume. If you go backwards, you're getting the amount of water that came in between two time periods.
Isn't that just the first derivative? Or like not the first derivative, just
The
the
original.
Oh,
Because
okay.
that's what we're working backwards
Yeah.
on.
Oh,
Okay,
so
we
they're
know,
gonna tell us how much
In
water
chemistry,
to
C of
us.
T could be the concentration at a given point in time. So the derivative of that is the rate of the reaction. So then going backwards would be the amount your product changed between two periods of time.
So let's do these problems.
We talked about some of these when we started with what is a derivative and how it applies. If you have the mass of a rod, okay, linear density is the derivative. So if you go backwards from the linear density, you're getting the actual mass between 2 points. Population growth, okay, growth is the rate of change. So if you know how fast the population is growing, if you do the integral between 2 points, you get the amount of change in your population between two endpoints. We use a lot of these same scenarios when I was saying what would a derivative be. It was the rate of change.
So it would be like if T2 was 4 and T1 was 3. It's no extra work, it's just explaining what.
Exactly. We've talked about marginal cost a lot, right? Marginal cost is a derivative. It tells us how the cost is changing. So if you integrate marginal cost, you get the actual change in cost. Not just the rate of change at a given point in time, but the actual dollar amount, the cost change between 2 points. Velocity. We know velocity is a derivative. So if you go backwards from velocity, what do you have? Position. So if you integrate between 2 points in time, you're getting the change in position over those 2 points in time. Alright, do you guys kind of understand the connection between those?
Yeah.
Last thing, and what we're going to pick up with Monday, is the difference between distance and displacement.
Beautiful.
Displacement is how far you are from your starting point. Okay, if I start right here at the edge of my desk, and I walk over here, and then I turn around, and I walk back, and I maybe go back and forth a few times. Displacement is when I stop, how far am I from where I began? Okay, I'm just like 3 feet from where I began. Distance is how far did I walk? So there's a difference, because I walked all the way over here, then I turn around, so you would add that, then I turn around, so you would add that, and then I came back here. So distance is like the absolute value. It's adding in everything. Whether you walk forwards or backwards, I want the distance I walked, so you would add them. Whereas displacement just tells you how far are you from where you began. We'll pick up with that on Monday. So, you have the 5.3 homework, which is due Monday. This homework, you could do a lot of it, probably all of it right now if you really felt so inclined.
Whoa, Jill.
It's a lot of integration that we've been doing.
Monday.